Right. So just take a few questions. We'll begin with some questions in the clusters. Write down the question. What is the structure of HFe3CO11 minus? This we have done. Fe3CO12 we have done. Try to find out the structure of HFe3CO11 minus. What is its structure? First, how many electron system is it? Count the electron system. Total electron count. 1 hydrogen is 1 electron. 3 irons, 24 electrons. 11 carbonyls, 22 electrons. So it is 47. 1 negative you have to add. It is a 48 electron system. So what will be the skeleton? Skeleton will be trigonal planar. So the skeleton of this is trigonal planar. Skeleton is trigonal planar. Out of 11 carbonyls, we have 4 plus 3 altogether 10. One carbonyl is bridging, and there is another hydrogen which is a bridging one. One mu carbonyl and one bridging hydrogen. One bridging carbonyl and one bridging hydrogen. This is a very, very important point. One bridging carbonyl and one bridging hydrogen. So here remember a point, whenever you have hydrogen, that hydrogen could be a terminal, or it could be a doubly bridging, or it could be a triply bridging bonding mode. So in this case you can find that the hydrogen is doubly bridging one. So you can also call it as edge bridging, because between the two irons there is an edge. That edge is being bridged by a hydrogen. We call it as edge bridged hydrogen. Sometimes it could be phase bridged, sometimes it could be terminal. Along with these 4 bonding modes, hydrogen can also be interstitial. Hydrogen can also be interstitial. So here hydrogen becomes completely different with respect to any other ligand. So just note down this point. Hydrogen, it could be terminal. Hydrogen could be terminal, or it could be edge bridging or doubly bridging. It could be phase bridging or triply bridging, or it could also be interstitial. It could also be interstitial. On these different bonding modes, I'll give you a few examples, but just before that, try to work out this example. Fe4CCO13. What is its total electron count? Fe4CCO13. All these are very important examples that I am giving you. What is the total electron count? 4 irons, 32 electrons, 1 carbon, 4 electrons, 13 carbonyls, 13 into 2, 26. No charges. So 26 plus 4, 30, 62. It is a 62 electron species. If it is a 62 electron species, what could be its structure? 62. Butterfly. Okay, so it has to be a butterfly. And whatever carbon that is present, that carbon is considered to be interstitial. This is hinge joint. Many times I have told you hinge joint. And for that hinge joint there is one bridging carbonyl. Okay. So out of 13 carbonyls, one is a bridging carbonyl, remaining are terminal. What is more important to remember is structure is butterfly. In that butterfly structure, but there is one bridging carbonyl. And another point to remember is it is a carbido cluster. You can see it is an interstitial cluster. Interstitial atom is carbon. Therefore, we consider it as a carbido cluster. Next example, Fe4CO13 2-. How many electron system is it? Total electron count 60. So 60 means what should be the geometry? Geometry should be tetrahedra. Total electron count is 60. Geometry is tetrahedra. In one of the previous exam questions, it was asked how many bridging carbonyls are present in it. Any answer? Anyone? How many bridging carbonyls? So do you remember the structure of CO4CO12? CO4CO12. How many bridging carbonyls were there? 3 bridging carbonyls. This is almost similar to that CO4CO12. Instead, we are putting Fe4CO13. So iron is altogether how many atoms for iron? Sorry, how many electrons? 8. 9, 10, 11. Just let me put it as 3. Let me put 3, 2, 2, and 2. So how many carbonyls are completed? 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. You just count the electrons. Count the electrons. Suppose if I count it for 12, 8 electrons for iron, 10, 12, 14, 15, 16, 17. Altogether there are 17 electrons. But there is a negative charge. 2 negative charges, I can take 1 negative charge for this. So this is a 18 electron system. For all these 3 irons, just let me count for 1 iron. Iron is 8, 9, 10, 11, 12, 13, 14, 15. It is 15. One is coming from this bridging carbonyl 16, one is coming from this bridging carbonyl 17. Okay, 16 and 17. So this also has 17, this also has 17. All these 3 ions should get one more electron. All the 3 ions should get one more electron. There is one negative charge. So count that one negative charge to one of the ions. For other 2 ions, there should be one more bridging carbonyl. And that bridging carbonyl is a triply bridging one. There is one triply bridging carbonyl. Whenever I draw this structure, it looks like a trigonal bipyramidal. But the skeleton is not trigonal bipyramidal. Skeleton is tetrahedra. One carbonyl is triply bridging, which is a phase bridging from the below. 3 carbonyls are doubly bridging. Okay, so how can we write it? Altogether, how many terminal carbonyls are there? 3, 4, 5, 6, 7, 8, 9. 9 terminal carbonyls. 1 bridging carbonyl, which is doubly bridging. 1 triply bridging carbonyl. Sorry, doubly bridging are 3. So 9 plus 3 plus 1, altogether 13 carbonyls. Okay. So whenever this structure is asked, what you should be remembering is structure is just similar to CO4, CO12. So what you have to put, just put 4 irons just as 4 cobalts. Put 3 bridging carbonyls which are doubly bridging. Remaining you just try to adjust them as terminal. 1 carbonyl will be triply bridging. It is just a phase bridging. So you put it from below. The structure looks like a trigonal bipyramidal. But skeletal structure is tetrahedra. Carbonyl is triply bridging from below. Nine terminal, 3 doubly bridging and 1 triply bridging. So many times these questions were asked, similar questions. Total electron count is easy, but they'll ask you how many bridging carbonyls are present, how many terminal carbonyls are present. Finished? Now please try to work out these structures. HRU6CO18 minus. Next one is H2RU6CO18. What could be their structures? What could be their structures? HRU6CO18, H2RU6CO18. This is minus, there is no charge in this. Is it closer, pseudo or arachno? You can go by the factor also. 6 into 3 is 18. How many pairs of electrons? 18. Hydrogen and negative charge will become 1. So n plus 1, it has to be closo. Same is this, n plus 1, closo. So what should be the structure? Structure should be closo, octahedra. Have we done for osmium 6CO18 2 minus? Just similar to that. But this is H and minus. Okay. Next. This is the skeleton. Okay. Now an important point is, where should you put the hydrogens? Where should I put the hydrogens? For the first one, it was found to be interstitial. So hydrogen is present in the center. Okay. It is a hydrido cluster. And in the second case, it was a previous CSR exam question asked for 4 marks. There are 2 hydrogens. These 2 hydrogens were not found to be terminal. They are not found to be doubly bridged, but they are found to be triply bridging. And triply bridging, suppose if I put one hydrogen, triply bridging means it will bridge a phase. It is bridging one phase, okay? Exactly the other hydrogen is bridging the trans phase. So 2 triangular phases which are trans to one another, they are bridged. 2 triply bridging hydrogens. In some literature you will find it as cis also. This is trans. Cis is also found. So you need not get confused. In some research articles it is given as trans. In some research articles it is given as cis. So both are found, cis as well as trans. How should you predict whether hydrogen, if it is present, should I go for interstitial, should I go for triply bridging, should I go for doubly bridging? It is very, very difficult. Okay, so you have to know the structures. No other go. You have to know the structures. Next example. First, let us take osmium H. Try to work out their structures. Did you got it? What are their structures? Closo, N+1, closo. Every example is a unique example. In this case, there was only one hydrogen which is found to be triply bridging. So whenever this example is given, I don't know whether I have to put it as interstitial, I don't know whether I have to put it as terminal, doubly bridging or triply bridging. So directly you have to learn the structures. Okay. Whenever the metal is ruthenium, the same single hydrogen was found to be interstitial. But whenever the metal is osmium, it is found to be triply bridging. That same hydrogen is found to be triply bridging. So why does that happen? We cannot tell. Because when compared with ruthenium, iron, ruthenium and osmium is larger, right? So whenever osmium is larger, whatever octahedra that is formed by osmium should be larger. So space inside should also be larger. It can easily take hydrogen. So what we generally think is hydrogen should be going inside because there is a larger space compared with ruthenium. But it is not so. Hydrogen is not entering inside. Instead, it is found to be triply bridging one. Okay. The last one, H2 osmium 6 CO18. Closo. Structure. Octahedra. So where will you put the hydrogens? Just you try to guess and try to put the hydrogens. H2 osmium 6 CO18. H2 osmium 6 CO18. Try to draw the structure of it. Any prediction? What could be the hydrogen? Terminal, or whether it is doubly bridging or triply bridging? Okay. What is this? Square pyramid. How many triangular faces are there? 4 triangular faces and 1 square face below. Just one of the triangular faces I am capping. You just watch. This is one. So one of the triangular faces which is towards your right, I am just capping it. This is called as capped square pyramid. What capped? Triangular face capped. Mono capped, but it is a triangular face. Square face is not capped, it is a triangular face capped. Okay. This is the structure of that cluster. H2 osmium 6 CO18, everyone might have drawn octahedra. Right? Structure is closure structure. And almost everyone might have drawn octahedra. But this is one exception for Wade's rules. PSEPT has failed in some structures. One of the best examples is this. Everyone predicts it to be octahedra, but it was not found to be octahedra. It was found to be monocapped square pyramid. Second point to be noted, the two hydrogens, they are present as edge bridging. So if this is the base of a square pyramid, for that base of a square pyramid, you can say this is one doubly bridging hydrogen, this is another doubly bridging hydrogen. So there are two doubly bridging hydrogens, okay, and it is a face capped square pyramid, which is a triangular face capped square pyramid. You just write down a point. First you take down the structure, very important one. Because of this, now we have a limitation for PSEPT also. Till this point we were working out all the structures nicely, but suddenly there is a limitation for PSEPT. Write down a point. The structure of H2 osmium 6 CO18, the structure of H2 osmium 6 CO18 is predicted to be octahedral skeleton. Is predicted to be octahedral skeleton according to PSEPT. According to PSEPT. But it is found to be, write down this, a non-octahedral hexanuclear osmium cluster. But it is found to be a non-octahedral hexanuclear osmium cluster. With a structure of triangular face capped square pyramid. With a structure of triangular face capped square pyramid. Triangular face capped square pyramid. Next, it has two edge bridging. It has two edge bridging hydrogens. That are cis to one another. It has two edge bridging hydrogens that are cis to one another. Okay. Next, it is a limitation for PSEPT. It is a limitation for PSEPT. Okay, it is a limitation for PSEPT. Next structure, H2 osmium 5 CO15. H2, osmium 5, CO15. First tell me what is the total electron count? How much is the total electron count? 2 hydrogens. This is 40 electrons. 15 carbonyls, 30 electrons. So I got a total electron count of 72. For how many metals? 5 metals. Whenever for 5 metals, if I get a total electron count of 72, what is the geometry predicted? TBP. The geometry has to be TBP. Suppose if it is 74, if it is 74, square pyramid. If it is 76, triangulated net. If it is 78, bow tie. Okay. So just I am drawing that TBP. This is the predicted structure. Okay. But what structure they found is completely different. Completely different means, now just imagine from a TBP, if I just remove one bond, I'm just removing one bond, then how do you see this structure as? If I'm just removing one bond, there is a tetrahedral core, there is a tetrahedral core, and this one is just hanging. Okay, so there is one more osmium which is just hanging. So it is no more a TBP, it is found to be edge-bridged tetrahedra. It is not a ligand. Usually carbonyl will be edge-bridging, hydrogen will be edge-bridging, but in this case there is a metal which is edge-bridging. So the structure is thought to be a TBP, but the actual structure was found to be edge-bridged tetrahedra. Okay, this is another limitation for PSEPT. Where are the 2 hydrogens? Now in this case the 2 hydrogens, you have to put them as doubly bridging. Just remember they were found to be edge bridging. Where should you put? Exactly to the edge which is opposite to this edge. Which edge? Where there is a osmium. So for this edge, what is opposite? This one is opposite. In symmetry I have shown you, for a tetrahedra, suppose if this is one edge, opposite is this, which is perpendicular to it. Okay. Suppose if I am taking this edge, where is the opposite? This one is opposite. If I am taking this edge, where is opposite? This one. Okay. So this is opposite. Wherever the osmium is bridged, exactly to the opposite edge, you have to put the 2 hydrogens which are doubly bridging. Right. Take down the structure, description. Did you draw the structure? Okay, draw the structure, I'll give you the description. It is very, very difficult for one theory to explain all the chemical findings in inorganic chemistry. So even in the coordination chemistry we have seen simple VBT did not explain, Werner's theory did not explain, so we went for VBT. VBT did not explain, CFT did not explain, we went for LFT or MOT. Okay. So finally we have ended at MOT. Write a point. The skeleton is predicted to be, TBP. The skeleton is predicted to be TBP. But only 8 metal-metal bonds are present. Only 8 metal-metal bonds are present. And it is not even square pyramid. And it is not even square pyramid. The structure is found to be edge-bridged tetrahedra. The structure is found to be edge-bridged tetrahedra, where one of the metal atoms is bridging where one of the metal atoms is bridging an edge. One of the metal atoms is bridging an edge. This is another exception. This is another exception for PACPT. Another exception for PACPT. Okay, next one. Now tell me the structure. Ni9CO18 2 minus. We are little bit moving to higher side. 9, altogether 9 metals. With the help of factor, can you tell me? 18 is the base. With the help of factor, how many pairs of electrons are there? N plus 1, so you call it as a closo. Closo, how many metals are there? 9. So expected geometry is, what is the expected geometry? Whenever there are 9 metal atoms, the expected geometry is monocapped. Last class we have discussed square antiprism. Monocapped square antiprism. Okay. Do the total electron count. How much have you done? 162. 162. Okay. 128 or 162? Okay, let me do it for myself. Total electron count 9 nickel. Each nickel will have 10 electrons. 18 carbonyls. 36 electrons. 2 negative charges. Two negative charges, 2 electrons. So how much is it? 90, 128. Total electron count is 128. Expected structure is monocapped square antiprism. Write a point now. First take down all those. What is this? Octahedra. It is an octahedra. Okay. Exactly over this octahedra, what I am doing is, I am putting another triangle. Exactly over this octahedra, I am putting a triangle. That triangle, can you see this triangle which is away from you? Just let me connect to that. So what structure are you getting? Blue is an octahedra. Along with this blue, just let me highlight this also. What structure is this? Trigonal prism. Yellow one is a trigonal prism. This one is a octahedra. So the structure is found to be fused octahedra with trigonal prism. Can PACPT explain this structure? No. According to PACPT, it will always give you monocapped square antiprism. But when you see this structure, it is not a monocapped square antiprism. It is instead a octahedra and a trigonal prism fused together. Okay. So again, this is one more exception. Structure is fused octahedra with a trigonal prism. Now, if you can remember in the last class, I have given you one theory. Theory is, suppose if I want to explain the structure of a new cluster which is unable to explain by PACPT, then we can go for fusing. Okay, what characters can fuse? Vertices can fuse, edges can fuse, faces can fuse. In this case, what is being fused? Face is fused. If this is a trigonal prism triangular face, this is octahedral triangular face. So two triangular faces are fusing. Okay. So it is a face fused. It is a face fused polyhedra. Okay. According to our theory. Now, is our theory right or wrong? Let us check. If I say it is a phase fused polyhedra or a condensed polyhedra, what should be the total electron count? How much is the total electron count you got? 128. So how do you get the 128? You have to take the individual total electron count of the two polyhedra, then subtract 48 from that. Okay. So what is the total electron count of individual polyhedra? If I take trigonal prism, what is the total electron count? 90. Trigonal prism is 90. TBP is 72. Whenever you get TBP, 72. Square pyramid, 74. Trigonal prism, 90 plus octahedra. Octahedra will give you 84 electron count. Okay, you can just go through the previous pages. In the table, magic numbers I've given you, octahedra will give you 84. But there are two negative charges. So I'm taking it as 86. I'm just taking it as 86. Total electron count of trigonal prism is 90. Octahedra with two electrons is, with two negative charges is 86. So 90 plus 86 is 90 plus 86 minus, how are they fused? With a triangular face. So how much should I subtract? 48. Is it giving you 128? You check. If at all it is giving 128, then whatever we have proposed is right. Is it giving 128? 90 plus 90 is 180, so 176. 176 minus 48. How much is it? You are getting 128. So whatever theory that they have proposed, which was not explained by PSEPT, it is also found to be true. For some higher clusters, if I am not able to explain according to PSEPT, then I can put forward one more theory. What is that theory? Maybe there are two polyhedras which are coming close and fusing. In this case, the structure is found to be fused octahedra with a trigonal prism. Okay, write down that point. This is another previous exam question. After this, I'll give you one more question, but it is not directly related to the how many carbonyls are cluster. They have directly asked for point group. What is the point group of the below cluster? Write a point. Ni9 CO18 2 minus. Ni9 CO18 2 minus has a fused polyhedral structure. Has a fused polyhedral structure. Fused polyhedral structure where a trigonal prism is fused with an octahedral triangular face. An octahedral triangular face. Next, the total electron count is also matching with the theory of the total electron count is also matching with the theory of condensed polyhedra. So what is the theory we have understood? Just get the total electron count for the individual polyhedra, add them, from that subtract the characteristic number. So characteristic number is 48 because they are fusing with a triangular face. Next one, PT19 CO22 4 minus. What is its point group? Any predictions? It is a very, very high nuclear carbonyl cluster. So in the beginning, if you could remember, we have classified the carbonyls into two types, clusters into two types. One is called as LNCC, another is called as HNCC. For LNCC, what are the metals? It is mostly from 2 to 4. For HNCC, mostly it is 5 to 9. But even for 9, there is a wrong. Okay? This is 19. Can you predict? Can you predict? Answer is no. So just can you draw some structure? Can you guess its point group? What could be the structure of platinum 19? First get me the total electron count. Tell me the total electron count. How much? Platinum belongs to nickel group, nickel, palladium and platinum. So 10 into 19, 190. Okay. Platinum is giving you 190. 190 plus 4 negative charges plus 44. So 190, how much is it? 2. 238. Total electron count is 238. Now even if you go with the factor, how much is N? N is 38. Because for nickel, the factor that I have given you is 2. Multiply 19 with 2. You get 38. But how many ligand pairs are there? 22 plus 2, 24. So this is 24. How many less? 14 or less. 14 or less means it is almost n minus 13. How much is it? N minus? Exactly n. N minus 14. So how much capped it should be? If it is n, monocapped. If it is n minus 1, bicapped. N minus 2, tricapped. N minus 3, tetracapped. So the number of caps goes on. N minus 14 means how many caps should you get? 15 caps you have to get. Okay, 15 caps. It means how many? Pentadeck capped. Okay, so just write down a point. According to PSEPT, the above structure, should be a pentadeck capped structure. Pentadeck capped structure. But it is very difficult. To understand the structure. But it is very difficult to understand the structure. Next. The actual structure is found to be pentagonal planar units capped in between. Pentagonal planar units capped in between. So just try to look at the structure. The easier way I am telling you. First, this is a pentagonal planar. If I directly draw the structure, you will get confused. So easiest way, pentagonal planar. How many I got altogether? 15. 5, 5, 5. Then 16, 17, 18, 19. So whatever that additional platinum that I have kept, you have to just join to that. That pentagon is joined to this. Next, this particular dot, you join it to the above pentagon. It is just like B12H12 2 minus structure. Do you remember? So you join it. Finished? Next, to this same vertex, you join this pentagon. Then to this vertex, you join this pentagon, above pentagon, below. So just let us continue. So to the same vertex, it is also joined. Now do the same with this. So likewise, I am just proceeding. Okay. Can anyone tell me the point group of this? Can you just tell me the point group? If you want, you can draw the structure, or else you may skip. But can you tell the point group? How are the three pentagons? Are they eclipsed or staggered? They are eclipsed. So what could be the point group? D5H. Point group is D5H. This was the question asked for 4 marks. So such rare questions may also come. It is very difficult for us to predict. If you want, you can draw the structure. The easier way I have told you. First put 3 pentagons. Above and below pentagon, you just put one more platinum. All these are platinums. So unpredictable the structures are. You have seen whatever structures that we have discussed today. So from here we will move on to a new and very important theory. Just write down a few points if you have drawn the structure. How to draw? 3 pentagons first you put. Above and below the pentagons you put one more atom. You just join that atom to the pentagon. From above, from below. It is just like a diamond kind of a structure. 3 diamonds are like fused. Point group belongs to D5H. So there is no base polyhedra. If you have noticed, there is no base polyhedra on which capping is occurring. If you see for osmium, if you can remember, osmium 6, osmium 7, osmium 8, osmium 9, osmium 10, we have done a table where we got a parent as octahedra. Then we have got it as monocapped, bicapped, tricapped and tetracapped. Do you remember these structures? Osmium 7 CO21, osmium 8 CO22 2 minus, osmium 9 CO24 2 minus, osmium 10 C CO24 2 minus. For all those, what we have done is we have taken a single parent polyhedra. Every time the parent polyhedra was capping, mono, bi, tri, tetra. But in this case there is no parent polyhedra. So where you can see 15 caps, no. It is a completely different structure. Okay, where PACPT totally fails. Neither can I nor can you, anyone can predict these structures. It is very difficult to predict. Directly I have to study the structure, then I have to give the conclusion. But I just cannot predict the structure as it is. Write down a point. There are several metal clusters. There are several metal clusters which were unexplained. There are several metal clusters which were unexplained by PACPT. By PACPT. Next, to explain some of the structures, a new theory was put forward. A new theory was put forward by Hoffman. You are aware of Hoffman, organic chemist. By Hoffman, which is called as Hoffman's isolobal analogy. Hoffman's isolobal analogy. Hofmann's isolobal analogy. Okay, just in 2 minutes I'll explain what is this Hofmann isolobal analogy. You are aware he is an organic chemistry scientist. Okay, so in the organic chemistry he has studied a lot about carbon and carbon containing units like CH3, CH2, CH and so on. What do I call CH3 as? I call it as methyl, I call it as methylene, I call it as methylidine or methylidine. Okay, so he has taken methyl, methylene and methylidine. For all this organic chemistry, what he has done is he has studied about HOMO and LUMO. What orbitals are HOMO, what orbitals are LUMO, how are they participating in a given chemical reaction. Okay, that he has studied. In a simpler way, suppose if I take one methyl radical, I'll add one more methyl radical to it. What will be the product? Product will be ethane. It is as simple as that. Okay, so in any particular chemical reaction of some organic chemistry entities like methyl, methylene or methylidine, he has studied the frontier orbitals called as HOMO and LUMO. After studying, he has given his analogy. What does his analogy tell? Suppose if I am taking an organic fragment like methyl, later I will take organometallic fragment. I am taking an organic fragment, I am taking organometallic fragment. Between these two, he has brought an analogy. What is that analogy? For your logical purpose, you just remember it as sense. Simply you remember it as sense. What is this sense means? Suppose if I am taking a methyl, there is one orbital. In its frontier, there is only one orbital which is taking up one electron into that. So if I take another organometallic fragment which also has a similar way, suppose if I am taking MnCO5 radical, it will also have a similar orbital in the frontier zone which is taking up one electron. There should be some matching features between these two fragments. What are these matching features? Just let us look here. Okay. In the frontier orbital, whatever lobes that are present, whatever orbitals that are present, their approximate shape must match. 1s for shape. Okay. 1s for symmetry. Symmetry of the orbital. Symmetry has to match. Suppose if it is like a sigma, this should be sigma. If that is a pi, this should be a pi. So symmetry must match. Their shape has to match. If one is of a sigma shape, another should be of a pi shape, or it is not so. Shapes has to match. Symmetry has to match. 1e represents approximate energy. Approximate energy means, suppose if I am taking a methyl, methyl is having a p orbital, 2p orbital. So if I am choosing a manganese, maybe it is a 3d orbital. Exact energies will never match, but approximate energies has to match. Of what? Of the frontier orbital. The frontier orbital energy of an organometallic fragment should be close to that of your organic fragment. Okay, so 1e represents approximate energy. Okay, next, what does n represent? Number of orbitals. Number of orbitals in the frontier zone. Suppose if I am choosing methylene, CH2, there are 2 electrons and these 2 electrons will be present in 2 different orbitals. So I just cannot make a match between these 2 orbitals with MnCO5, because in MnCO5 there is only 1 electron lodged in a single orbital. In methylene there are 2 electrons lodged in 2 different orbitals. So I just cannot match with these 2. So the number of orbitals should also match. Okay, if I am choosing an organometallic fragment and an organic fragment, between these 2 in the frontier zone, how many number of orbitals are there? That has to match. What is the shape of those orbitals? That has to match. What is the symmetry of those orbitals? That has to match. Approximate energies have to match. They need not be same. They need not be same. But approximate energies must match. And finally, E represents electrons. The electrons present in them should be similar. They need not be identical. Okay? That is the final statement that he has given. So this is a very important statement. The final statement is the total number of electrons present in those frontier orbitals, they have to be similar. They need not be identical. Getting the point? So based on this, what we tell is, you might have heard about, suppose if I am taking a 7 electron system, we say it is isolobal to 17 electron system. What is the basis for saying this? This 7 electron system is an organic fragment. This 17 electron system is an organometallic fragment. Okay, there are d orbitals in this. These two, I can call it as isolobal. When can I call it as an isolobal? Whenever their number of orbitals present in the frontier zone, their shapes of the orbitals, their symmetry of the orbitals, approximate energy, and the electrons occupying them should be similar, they need not be identical. Then I can call them as isolobal. Okay. For isolobal symbol is, you have to put an arrow, double-headed arrow. For that double-headed arrow, you have to put a lobe. One lobe, orbital like. Okay. So this we call it as isolobal. Isolobal. It means same type of lobes. The shape of the lobe, approximate energy of the lobe, symmetry of the lobe, number of lobes, and the electrons present in them should be similar, they need not be identical. Got the point? So whenever they match, then whatever chemistry that this organic fragment has, similar chemistry your organometallic fragment will also have. That is the analogy of Hoffman. Got the point? So if I just ask you, CS3 radical will combine to give you ethane. Now MnCO5, is it similar to methyl? Yes. Suppose if I combine these two, what should you get? I have to get Mn2CO10. Now in reality, do you have Mn2CO10? In reality, do you have Mn2CO10 or not? We have it. We have done the point group also. Do you remember? Mn2CO10. Forgot? Point group is D4D. So Mn2CO10 is also existing. Okay. So how an organic fragment behaves, in a similar way organometallic fragment also behaves. So the chemistry of your organometallic fragment can be dictated by knowing the chemistry of your organic fragment. Then I can call those two fragments are isolobal. For calling two fragments as isolobal, he has given some characters. Okay, so first write down this Hoffman isolobal analogy. Hoffman isolobal analogy. Hoffman has worked a lot. Hoffman has worked a lot in the field of organic chemistry. In the field of organic chemistry. In the field of organic chemistry. Next, the frontier orbitals means HOMO and LUMO. The frontier orbitals of organic fragments, were clearly studied. The frontier orbitals of organic fragments were clearly studied and were compared, WERE, and were compared with the frontier orbitals of organometallic fragment. Next, to say that two fragments are isolobal, comma, the number of lobes in the frontier region, of both the fragments comma, their shape THEIR, their shape, comma, their symmetry comma, approximate energies and the number of electrons occupying them must be similar. They need not be identical. Must be similar. They need not be identical. They need not be identical. Next. The three important fragments considered are write down this: methyl, methylene and methylidyne. Methyl, methylene and methylidyne. If I ask you how many electron system are they? How many electron system are they? This is 4 plus 3. It is a 7 electron system. 4 plus 2, 6 electron system. 4 plus 1, 5 electron system. So a methyl is a 7 electron system, methylene is a 6 electron system, methylidyne is a 5 electron system. This we have to match with organometallic fragment. Methyl, methylene and methylidyne. Okay. Next point. According to this analogy, a 7 electron system is a 7 electron system of organic fragment is isolobal with 17 electron system of an organometallic fragment. 17 electron system of an organometallic fragment. Next. The symbol of isolobality is given by a double-headed arrow with a half lobe indicated at the center of the arrow. With a half lobe indicated at the center of the arrow. Half lobe means, suppose if I am choosing a p orbital, maybe from that p orbital just a half lobe. So all these electron systems are isolobal. What is the meaning of it? Whatever I have written. Suppose if I am choosing a 3 electron system, one such 3 electron system can be isolobal to another 3 electron system, or that 3 electron system can be isolobal to a 13 electron system. This 13 electron system can be isolobal to another 13 electron system. Okay, that is the meaning of it. How should you understand this? Now just suppose if I give you MnCO5, how many electron system is it? How many electron system? Simply you have to count the valency electrons, 7 plus 5 into 2. It is a 17 electron system. It is isolobal with which organic fragment? 17 is isolobal with 7. 7 means I take a methyl. So MnCO5 is isolobal with 7 electron system. This can be isolobal with a BH4? Because if this is 4 plus 3, 7, this is 3 plus 4, 7. So 7 electron is isolable with another 7 electron system. 17 electron can be isolable with another 17 electron system. Technetium CO5, manganese CO5, technetium CO5, rhenium CO5, 17 electron system. So one 17 electron system can be isolable to another 17 electron system. It can be isolable to 7. It can be isolable to another 7 electron system and so on. Okay. First take down these points. I'll give you examples separately. This will be very, very interesting analogy, and 4 marks questions can come from this topic. Very short topic, but many times 4 marks questions have appeared from this Hoffman isolable analogy. Is it an easy analogy or not? 7 to 17, 6 to 16, 5 to 15, 4 to 14, 3 to 13 and so on. Suppose if I start from a methyl, can I say methyl is isolable to MnCO5? Yes? Methyl is isolable to MnCO5? Okay. Manganese, you just take one more metal. If I take iron, what should I take here? It should be a 17 electron system. Try to put it in such a way. So MnCO5, manganese, iron, 1 electron has increased. 1 electron has increased. So what I'll do, I'll put 4. When I put it as 4, 8 plus 8 is 16. But I should get one more electron. So to get one more electron, you can take a negative charge. You can take a negative charge. Then these two fragments will also become isolobal. Okay. So what is one guideline we got? Suppose if I'm choosing one 17 electron system, I can choose another 17 electron system where the charges can be different. Charges can be different, but the number of electrons should be the same. This is a neutral species. This is a negative species, but both are 17 electron species, and they are called to be isolobal. Okay. Next, after iron, suppose if I take cobalt, I'll take COCO4. If I take nickel, I have to take NiCO3 minus, because nickel is 10, 3 carbonyls is 16, 1 negative charge 17. All these are isolobal. Okay. And finally, is there any other main group element which has 7 electrons? Which has 7 electrons? Main group element, iodine. So this is isolable with chlorine. Chlorine is isolable with bromine. Bromine is isolable with iodine. All these are considered to be isolobal. Okay, take down these examples. In a similar way, can you write for methyl? I say manganese CO5. Instead of manganese CO5, can I write rhenium CO5? Rhenium CO5. Can I write technetium CO5? Yes, because all group members have same electrons. Okay. Suppose if I want to write manganese, how many carbonyls should I put? CH2, this is a 7 electron system. You can just write somewhere 7 electron system. This is a 6 electron system. This should be 16. 16 means MnCO5 is 17. So I can take a 4, I can put a minus. Or I can take MnCO5, I have to put a plus. Next, Fe. Directly FeCO4. This example is an important example. This is an important example. I'm giving you more, but these are important examples which come across in exams. Next, cobalt, CO3 minus, nickel, CO3. If I want to take any main group elements, oxygen, sulfur, selenium, tellurium. Don't take polonium because polonium is radioactive. Next, one more example we'll take. CH, it is a 5 electron system. 5 electron system must be isolable with a 15 electron system. So if I take Mn, already it is giving you 7. I can take MnCO4, 8 plus 7 is 15. So they are isolable. Next Fe, CO3 minus CO, CO3, Ni, CO2 minus, and it is isolable with nitrogen, arsenic, so just write down the group elements finally. But for oxygen group, don't write polonium because it is radioactive. Suppose if I take a simple carbon, it is isolable with 4 electrons, means it can be isolable with a BH. It can be isolable with a BH unit. BH unit can be isolable with, again all these units you can write. Every time I am not writing those units, you can understand. But just let me write parallel to carbon. Carbon, silicon, germanium, tin and lead. All these can be considered as isolable. Next I am taking directly boron, 3 electron system. This is a 4 electron system. Boron can be isolable with aluminium, gallium, indium, thallium. All these units are considered to be isolable. We are just extending the theory, because in isolable analogy what Hoffman has told is approximate energies have to match. But you can understand here the approximate energies, they don't match very close. Energy of boron, energy of thallium is lot different. Energy of manganese, energy of technetium is lot different. Manganese rhenium is different. But still, for explanation purpose, we are taking. Once you take down this, I'll give you a previous CSR exam question. You try to work out, you will come to know how to understand this Hoffman isolable analogy. And mostly it will be asked for 4 marks, remember. So just by looking at it, you can answer. You just go through the examples, looking at it, you try to answer. CH is isolable to which BH unit? A CH is isolable to which BH unit? BH2. Because if carbon is isolable with BH. Let me take now carbon and BH. Okay. Carbon is isolable with a BH unit. Suppose if I take a CH, it is isolable with a BH2 unit. If I take a CH2, it is isolable with a BH3 unit. Suppose if I take a CH3, it is isolable with a BH4 or a BH3 minus. I can take a BH3 minus. 3 plus 3 plus 1, 7. 4 plus 3, 7. Even these are isolable units. Okay, take down this. So based on this, let me give you the previous exam question. All those examples are done? Previous examples. Not done? Write the question. It will be, according to PSEPT, according to PSEPT, what are the structures of, according to PSEPT, what are the structures of the given borane clusters, the given borane clusters. Well, take it as B4H8, B3H7, try to calculate their structures. One is B5H9, one is B4H8 FeCO3, one is B3H7 FeCO3 taken twice. What are their structures? Any answer? Which one? All are nido. All are nido, sure? First one, what is the difference? N plus 2, it is nido. Next one, I am taking it as B4H8. I am taking it as B4H8. What is the other fragment? FeCO3. FeCO3 means how many electron system? 8 plus 14. 14 electron system is isolable with a 4 electron system. So everything you convert it into borane terms. Because the question is about borane, everything you convert into borane terms. So FeCO3 is isolable with BH. So this plus a BH. Okay, that is your question. Next one, B3H7 plus how many FeCO3s? 2 FeCO3s. Each FeCO3 unit is isolable with, in the previous one, you just see, in the previous one, FeCO3 is isolable with CH, CH or C? C. A C is isolable with BH. A C is isolable with a BH. So put all into a BH term. Okay. So how many BH are there? 2. There are 2 FeCO3 means altogether there are 2 BH. So altogether how many borons? How many borons altogether? B5. How many hydrogens? 9. So B5H9, B5H9. Next. How many borons? 5. How many hydrogens? 7 plus 2. It means all the 3 belong to nido. So what is the question based upon? Hoffman isolable analogy. Okay. They have given you FeCO3. FeCO3 is a 14 electron system. 14 electron system is isolable with a 4 electron system. 4 electron system is a carbon. But I am trying to put it into borane terms. So Hc is isolable with a BH. BH is a 4 electron system. So everything I am putting into a borane. Now simply I am getting B5H9. It is a nido. B5H9, it is also a nido structure. Okay. So that is how you have to work out. You can just do it. Write down a point. When an organometallic fragment is given, when an organometallic fragment is given in a borane cluster, in a borane cluster, comma, convert it into the corresponding borane. Convert it into the corresponding borane by using isolobal analogy. By using isolobal analogy. By using isolobal analogy. Okay, now you just put this N+2 before H8 plus BH and so on. I'll just draw a table, then I'll give you a break. Let me see how many of you can understand this table. Before H8 plus BH, B3H7 plus 2BH, it is equivalent to a B5H9. So all are nido. Okay. So here what am I doing is I am just comparing an organic fragment with an organometallic fragment. What is the coordination number of that organometallic fragment? It could be 9, it could be 8, 7, 6 or 5. Let me take an example. With one example we'll begin. Suppose if I am taking a D1 Ml8, I am taking an organometallic compound which is a D1 Ml8. When I say D1 Ml8, what is the total coordination number of it? Altogether there are 8 ligands. Along with this 8 ligand, in the frontier zone, there is 1 electron in a lobe. So I consider it to be a 9. Altogether 9. That is one way to understand. The second way, it is a 7 electron system. This should be 17 electron. How do you get 17 electron? Every ligand is considered to be a 2 electron donor. So 8 into 2, 16. In the frontier zone, how many electrons you have? 1. So 16 plus 1, 17. So wherever I take D1 Ml8, that is isolobal with your methyl. Okay, I'll just fill the table. You can do it parallelly. Simultaneously you do it. And once you complete this table, you just try to understand it. This is the table given from Hoffman studies. Okay. What I'll do is I'll just extend little bit for our understanding purpose. But up till this only it has been given in the literature. Okay. For our understanding, whatever I am putting, it is just for our understanding. I am taking a 4 electron, I am also taking a 3 electron system. I am taking 4 electron as a carbon, I am taking 3 electron as a simple boron. Okay, a boron is a 3 electron system. What do you understand from this table? Anyone? What do you understand from this table? For the first time when I saw this table, I did not understand anything. I'm just looking at D6ML5, that is comparable to something else. What is that? Have you completed? First line, did you complete? Okay. Just one or two implications, then I'll put it on the board. We'll go for a break. Okay. Just look here once. MnCO5. MnCO5. Is it Ml5? Yes. It is Ml5. How many electron system is it? D7. So it is a D7Ml5. Where do you find D7Ml5? I find D7Ml5 here. So D7Ml5 is isolable with 7 electron system. It means it is isolable with methyl. Getting my point? Okay. So MnCO5 is isolable with this particular unit. Suppose if I say FeCO3. What is FeCO3? Iron is D8Ml3. So you just see where is D8Ml3. D8Ml3. So D8Ml3 should be equivalent to a 4 electron system. It means this is a 14 electron system. It is isolable with a 4 electron system. So C is isolable with which boron unit? BH. So if I give you FeCO3, it is isolable with carbon. Carbon is isolable with BH. Now did you get the previous CSR exam question? They have given you FeCO3. Where do you find that FeCO3? D8Ml3. D8Ml3 is 4 electron system. So you need not remember this table. Whenever you get D8Ml3, they have given you this. When they have given you this, simply you take it as D8Ml3. How many electron system? 8 electrons plus 6 electrons. It is a 14 electron system. 14 electron system must be isolable with. So 4 electron system boron unit is. So simply FeCO3 they have given you. You have to convert it into BH. Okay. Simply convert it into BH. Suppose they give you MnCO5. You can correspondingly convert into. Suppose they have given you MnCO5. It is isolable to which BH unit? It is 17 electron system. It should be equivalent to a 7 electron system. I take a BH. How many electron system is it? 4. So if I add BH3, 3 plus 3, 6 plus 1, 7. Or I may take a BH4 unit. Getting my point? So this table will help you in that case. Okay. Just take down the table. We'll go for a 5-minute break. Then we'll continue. So tomorrow also I'll take a similar way, 2:30 till 5 or 5:30. Maybe in 2 to 3 days we'll complete these clusters. Halide clusters are another important topic. We'll complete that topic possibly by tomorrow. So just write down a few guidelines. As per the analogy, the following considerations can be made. First one, group members with identical electron system can be considered as isolobal. Example, you just take down this example. Group members are isolobal. In a short way, group members are isolobal. Manganese, technetium, rhenium are isolobal. So in the place of manganese CO5, I can replace it with a technetium CO5, or I can replace it with a rhenium CO5, and so on. So simple conclusion is group members are isolobal. This example. Next. A two electron ligand can be replaced. A two electron ligand can be replaced by two charges or two hydrogens or by a charge and a hydrogen. Two charges or by two hydrogens or by a charge and a hydrogen, comma, all such fragments are considered isolobal. Take down this second example. If I take FeCO4, how many electron system it is? 8 plus 8, 16 electron system. It is a 16 electron system. 8 plus 6, 14 plus 2. Again, this is a 16 electron system. 8 plus 6, hydrogen is 1, electron is 1. So all are 16 electron system. As far as I maintain this isoelectronic rule, I can go on writing different fragments. All are considered to be isolobal. So I can replace a carbonyl with another 2 electron ligand. That is also, suppose in the place of carbonyl, suppose suddenly I write PPH3. That is also considered as isolobal, because PPH3 is also taken as a 2 electron donor. That does not change the electron count. Okay. Next one, if I take a CO3, how many electron system it is? 15 electron system. In general, organometallic chemistry, a nitrosyl is considered as a 3 electron donor. Okay. So I can replace a carbonyl with a nitrosyl by a proper charge replacement. Suppose if I take 2 carbonyls, 4 electrons, I replace it with a nitrosyl, 3 electron. Then how many electron system it is becoming? Nickel is 10, this is plus 2, 9 plus 6 is 15, 10 plus 2 plus 3 is 15. So I can make a proper charge replacement once I replace carbonyls with nitrosyls. Now this is also isolobal. This is cobalt. In this case, metal is different, but the number of electrons is same. 9 plus 6 is 15, 10 plus 2 plus 3 is 15. provided nitrosyl is considered as a 3-electron donor. In organometallic chemistry, for most of the clusters, nitrosyl is taken as 3-electron donor only. Okay, write down the third guideline. NO can replace CO. NO can replace CO with proper charge substitution. With proper charge substitution. With proper charge substitution. Example, COCO3 and NiCONO. They are considered as isolobal. So with respect to analogy, implications, where do we apply them? We have to study. Implications. First one, write down this. A methyl is isolable with a MnCO5 unit. So what are the applications of your analogy? How organic fragment behaves in a similar way, organometallic fragment should also behave. That is the implication or application of your analogy. Let us check. Suppose if I combine a methyl plus another methyl, this will give you ethane. Likewise, if I combine an MnCO5 unit with another MnCO5 unit, I should get a similar structure. Okay? And once they have done the reaction, they were getting a similar structure also. So I can tell that this analogy is working. Do you have Mn2CO10? In the organometallic chemistry, do you have Mn2CO10? Yes, we have it. It means analogy is working. Next, MnCO5, it is isolobable with methyl. So can I make a reaction with MnCO5 with methyl? Can I perform a reaction between MnCO5 and a methyl? If at all I perform, what should I get? This is what I have to get. And practically they were getting this also. Practically they were getting this. It means again my analogy is working. Next, manganese is isolobable with its group member. So if I take technetium or even rhenium, and if I combine this rhenium with a methyl, what should you get? This is actually a lobe, don't get confused. Lobe with an electron. What should I get? Technetium CO5 with a methyl, and even this they were getting. So what is the implication? Whatever Hoffman isolobal analogy has predicted, most of the predictions are true. Okay? Take down these examples. If a methyl is able to combine with another methyl to give you ethane, MnCO5 can also combine with another MnCO5 to give you Mn2CO10. MnCO5 is isolobable with another methyl, therefore they two can merge, or technetium and methyl can merge, or I may take a MnCO5. Can I combine with it a technetium CO5 or a rhenium CO5? It is also possible. And they have performed all these reactions. They got the products. It means Hoffman isolobal analogy is working. Instead of technetium, you can also take rhenium. Every example you need not take. You can just understand the implication. Analogy is working. Every time you need not put this lobe and an electron. Once if you put, you can understand. If I take a methyl, it is a 7 electron system. It is isolobable with a 17 electron system. So a 7 or a 7 electron system can combine. A 17 or a 17 can combine. 17 or a 7 can combine, and so on. finished. Let me take one more example. A CH2 is isolable with FeCO4. Is it isolable or not? 4 plus 2, it is a 6 electron system. 8 plus 8, it is a 16 electron system. Therefore, they are isolable. So, if I take a CH2, I take another methylene, what will you get? If I combine both, what do you get? You will get ethene. Likewise, if I combine FeCO4 with another FeCO4, what should be my product? It has to be Fe double bond FeCO4 and CO4. That should be my product. Okay. You write it as stable at low temperature. It was formed, but it is only stable at low temperature. It was not stable at higher temperature. Any other way that you can combine a methylene with another methylene? Any other way? Remaining ways you can just go through. Every reaction I am not giving you. Suppose if I take FeCO4, I combine with a CH2. What should be your product? FeCO4 double bond CH2. Next, FeCO4 is isolable with ruthenium CO4. Ruthenium CO4 is isolable with osmium CO4. So you can combine all those units. All such products are also formed. I am not writing each and every reaction. I am just writing the product. Suppose if I take FeCO4, you may get osmium CO4. I may take ruthenium CO4. I may take another ruthenium CO4. Or in the place of one ruthenium, you can put osmium. All such combinations are possible. Okay. Suppose if I combine two methylenes in this way, what do you get? Instead of two methylenes combining, let me combine 3. What are you getting? You are getting a cyclopropane. So in a similar way, a methylene is isolable to FeCO3. So if I combine 3 FeCO3 units, a similar structure has to form. Do you have such a similar structure in your organometallic chemistry? Yes or no? We have Fe3CO12, Fe3CO12, which is a triangular shape, right? So can I predict this structure? Yes. But what is the difference? In reality, you are having 2 bridging carbonyls. But this is only able to predict the skeleton. Okay? If 3 methylenes, if I combine, it can give you a cyclopropane kind of a structure. 3 FeCO3 should also give you a metallocyclopropane kind of a structure. That is what one implication is. This is called as metallocyclopropane. So that is according to analogy. Is it present in your organometallic chemistry? Yes, it is present. The skeleton is present, but the carbonyls are arranged differently. There are 2 bridging carbonyls. Okay, but this is being formed. Next, FeCO3 is isolable with a CH2. So in the place of a CH2, can I write FeCO3? Yes or no? In the place of a CH2, I can write FeCO3. So this can be one structure. Or iron is isolable with ruthenium. So ruthenium CO3 is also expected. This structure also can be prepared. Or I can prepare is it present? Are they isolable or not? Is CH2 isolable with iron? Yes. So in the place of CH2 I can replace FeCO3. CS2, CS2, FeCO3 is isolable to its group members. So in the place of iron I can replace with ruthenium or osmium. I have put ruthenium. Or I can replace completely with rutheniums. This is present. We have seen the structure also. Or in the place of ruthenium and all the three irons, I can just put iron, ruthenium and osmium. This is also a possibility. All these possibilities we can draw. Okay. How many of them really exist, we have to check every time. And according to the practical data, most of the structures were existing. That is one of the best implications of Hofmann's isolable analogy. Whatever he has predicted by taking the organic fragment and comparing it with the organometallic fragment, whatever structures they were getting, most of them were also practically found. Okay? When we go to the next stage, there is another CSR exam question which was asked. That example will come here. So how to answer such a question means from Hofmann isolable analogy. If I take a methylidine, I combine with another methylidine, what do you get? If I combine them, what should you get? Acetylene. Likewise, it is isolable with which fragment? Can I take COCO3? How many electron system it is? 5 electron. This is 9 plus 6, 15 electron. So a 5 electron system is isolable with a 15 electron system. In the place of CH, can I take COCO3? If I take a COCO3 and if I combine with another COCO3, what should be my product? The product has to be CO, triple bond CO, CO3. That should be my product according to Hofmann isolable analogy. Okay? Are you taking it down simultaneously? It is just a simple analogy. In the place of a CH2, you try to replace another isolable unit of your choice. In the table I have given you many units. Of your choice you choose. But the most common ones are MnCO5 for 17 electron system, FeCO4 for 16 electron system, COCO3 for 15 electron system. These examples you can find in most of the standard textbooks. So I am taking the same. Is there any other way a methylidine can combine with another methylidine? Any other way? Suppose if I take a simple methyl, combines with another methyl, completed. If I take a methylene, 2 methylenes can combine to give you a double bond, or 3 methylenes can combine to give you a triangle kind of a structure. In a similar way, can methylidines combine in any different way? Any other way? No? No choice? I am putting a CH. I am putting a CH. How many electrons are present? Just try to put the bonds. One bond between this, one bond between this, one bond, one bond, one bond, one bond. So what structure are you getting? You are getting a tetrahedral structure. If I take 4 methylidines, I can get a tetrahedral structure. A methylidine is isolable with which unit? CO? COCO3 unit. So in the place of a CH, can I replace it with a COCO3? Let me replace. So that should also give you a tetrahedral skeleton. Is it there in your organometallic chemistry, CO4, CO12? Yes, it is existing. But the only difference was there were 3 bridging carbonyls at room temperature. If I take it to higher temperature, that will be terminal only. So this is also existing. Next, in the place of cobalt, what structures can I replace? In the place of cobalt, I can just replace with a CH. I can put remaining 3 cobalts. Now this is your previous exam question. The question was, what is the bridging structure? Methylidine. Is it a doubly bridging, is it terminal, is it triply bridging, or what is it? CH. CH is triply bridging. You have a triply bridging CH. And this was previous CSR exam question. So how should you understand that? It is just an implication of your Hoffman isolobal analogy, where a CO-CO3 unit, which is 9 plus 6, a 15 electron system, is isolobal with a 5 electron system. So in the place of a CO-CO3, I can simply replace it by a CH. That CH is making 3 bonds with 3 metals. Therefore, I can call it as a triply bridging methylidine. Okay? How many electron system is it? What is the total electron count? What is the total electron count? CO4, CO12, what is the total electron count? 60. Total electron count is 60. What should be the total electron count of this? Okay. Or at least tell me, around each cobalt, is it obeying 18 electron rule or not? Yes. 9, 15, 16, 17, 18. This is also obeying 18. This is also obeying 18. All these are transition group elements. Carbon, main group element. So it has to obey 8 electron rule or octet rule. How many? 4, 5, 6, 7, 8. It means either 8 or 18 electron rule is being obeyed. Okay. So in the place of cobalt, if I can replace with iridium, can I write this cluster? Is it present? In your organometallic chemistry, is it present or not? Yes, we have seen it. There was no bridging carbonyl also for this. We have taken cobalt, rhodium and iridium, where we have seen for cobalt and rhodium, 3 bridging carbonyls were there. For iridium, there was no bridging carbonyl. And even this can be predicted. How beautiful the implications are, you can understand. All these are practically present. You can write at least 100 such examples. In the place of cobalt, you replace iridium. In the place of iridium, you replace rhodium. In the place of rhodium, you replace it with a CH. Or a CH can be replaced by a BH2 unit. All these are isolobal units. You can write hundreds of structures. But there are some limitations also. What are these limitations? First limitation, it can give you an idea about a skeleton. It can only give you an idea about skeleton, but it cannot give you an idea about how the carbonyls are arranged. Because in the case of which one we have seen CO-CO3, the actual structure at room temperature has got 3 bridging carbonyls. But according to this prediction, we generally don't draw any bridging carbonyls. Okay, so that is one limitation. Second very important limitation is when you combine 2 CH2s, what do you get? You will be getting ethylene. And whenever you are combining 2 FeCO4s, you are getting Fe2CO8. Okay, this is stable only at low temperature. So if I just take ethylene and this Fe2CO8, I'm taking ethylene and Fe2CO8, I'll add carbonyl to this. Carbonyl insertion between ethylene is not that easy under normal temperature and conditions. You have to maintain separate conditions. But whereas for Fe2CO8, immediate addition will occur. As and when you are adding a CO, it will immediately take up that and it will be forming Fe2CO9. Structure we have already seen. What is the structure of Fe2CO9? Confacial bioctahedra. 2 octahedrons are sharing a common triangular face. So I'm taking an ethylene. CO insertion is not easy. in the organic chemistry, but whenever I'm taking an Fe2CO8, it is stable at a very low temperature, but at normal room temperature and conditions, it is less stable. So whenever I add a carbonyl, immediately the cluster will change its structure into Fe2CO9. So this is not explained by analogy. Why it is so unstable and why carbonyl addition is so easy for this, whereas carbonyl addition is very, very difficult for this. Though they are isolable, such explanation is not given by Hoffman. This is second important limitation. Okay, you just take down first these two limitations. Limitations. First one. The structure predicted by analogy. The structure predicted by analogy has a correct skeleton. Has a correct skeleton in most of the cases. Has a correct skeleton in most of the cases. But how the bridging carbonyls arrange, how the carbonyls arrange, not bridging, how the carbonyls arrange is not predicted. How the carbonyls arrange is not predicted by Hoffman. Is not predicted by Hoffman. Next. FeCO4 easily combine with another FeCO4 to give Fe2CO8, which is unstable at room temperature. CO insertion, continue. CO insertion occur very easily. CO insertion occur very easily across a double bond. CO insertion occur very easily across a double bond. The same is not the case. The same is not the case with ethylene. The same is not the case with ethylene. This is unexplained. This is unexplained. Next, what is the other limitation? Have you seen the explanation of very complex structures like Ni9CO8 in 2- or why H2 osmium 5 CO15 structure is predicted one thing, but instead of a TBP you are getting a edge bridged tetrahedra. Why are you getting that? That is not addressed. Or hexanuclear, non-octahedral hexanuclear osmium clusters. Why are they coming? There was no proper explanation for that. Okay, so that can also be taken as a limitation. Write down the final limitation. The unusual structures not explained by PSEPT. The unusual structures not explained by PSEPT were 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 not addressed by Hoffman. Were not addressed by Hoffman. Not addressed by Hoffman. Okay, so these are the limitations that we have seen in the Hoffman isolobal analogy, right? So this ends the clusters. Okay, what clusters? Carbonyl clusters. We have to still take up halide clusters. We have to still take up boron clusters. Halide clusters, boron clusters. Halide clusters, there are very important questions. Topic is a very short topic, but there are pretty important questions in it. And finally, we have to come to borons. Boron clusters, we have to describe. Closer nude arachno, we have already done half of it. And the most important point is STYX, STYX, STYX code. In most of the exams, especially GATE or even CSR or JAM, they'll give you one particular boron. They'll ask you what is the STYX code, 2002. Is the STYX code for which boron? Or some B4H8, what is the STYX code? So how to find out that STYX code? What will be the number of BHB bonds? What is the number of BH bonds? All those things we have to see. Okay. But coming to the conclusion of these clusters, we have seen many carbonyl clusters. What clusters you have seen the most? Which metal is most participating? Osmium. Most examples are with osmium. Okay, so that is an important finding. Most of the organometallic clusters, especially carbonyl clusters, were formed by osmium. Okay, next. How many clusters have you seen with early transition metals? Early transition metals, scandium, titanium, vanadium, or chromium, all these are early transition metals. How many? Very little. But later transition metals, iron, cobalt, rhodium, iridium, osmium, many. So early transition elements are forming very less number of carbonyl clusters, whereas later transition elements are forming more number of carbonyl clusters. What is the reason for this? Any reason? Or let us come to a different topic. Just let me convert it into a topic. What factors favor a cluster formation, especially carbonyl cluster, what we have discussed? What factors favor cluster formation? We are just concluding all these clusters. Size, okay, that is one. High nuclearity is related to size. Now just try to understand the concepts. First concept, always remember, low nuclear charge. Low nuclear charge. Whatever clusters you have seen, how many clusters have you seen with a greater charge? Very less. You have seen clusters with a very less charge. FeCO4. Very rarely you find FeCO4 2-. But you don't find very high charge, 3+, 4+, 2+. Very rare you find. 1 or 2 examples. Right? But most of the clusters will be neutral. Or the metal will not have a higher charge. The metal will not have a higher charge. The simplest reason is, always the metal should be in a lower oxidation state, not a higher oxidation state. So the first factor that favor the cluster formation is low formal oxidation state. If the oxidation state of the metal is lower, what will happen? There will be more number of electrons in the metal. Metal will become more basic. More basic metal will give you more electrons. Stronger will be the bonding between the metal and the carbonyl because it is a multiple bond. There is a retrodative bond, back bonding. So ligand is giving, and if metal is more basic, metal is also back giving. We call it as a retrodative bond, and the multiple bonding will be more stronger. So always a metal with a low formal oxidation state will have more basicity, more number of electrons, and it can give you more electrons into the metal. Multiple bonding will be stronger, therefore cluster stability will be larger. Okay, so what is the first factor? Low formal oxidation state. Right. Let us take the second factor. Less number of electrons. Generally, less number of electrons is considered to be another factor. I'll give you these 4 factors. Less number of electrons is considered to be another factor. Why less number of electrons is taken as a stability factor? Less number of electrons is generally taken as a stability factor. We are just concluding. Though we have seen more electron systems, but a general factor is less number of electrons will favor cluster formation. The simple reason is, just imagine a metal has less number of electrons. In the beginning classes we discussed. If it has less number of electrons, the electrons will enter into bonding orbitals. If the number of electrons increase, they even enter into antibonding orbitals. As the electrons enter into antibonding orbitals, what will happen to bond order? Decrease. As bond order decreases, stability also decreases. Therefore, you will be finding those metals which has less number of electrons which favor the cluster formation. But suppose if the metal is having more number of electrons, what should I do? Then there should be a ligand which will take away that electron density so that more amount of electron density is not entering into antibonding orbital. What type of ligand is that? Carbonyl. Carbonyl is one of the best pi acids which will take away more electron density from the metal, where the stability of the cluster will be seen. So whatever carbonyl cluster that you have found, where you find most of the later transition elements which have more number of electrons, they are still stable. The simplest reason is carbonyl is a strong pi acid. So whatever excess electron density that the metal has, all that excess electron density will be taken away by the ligands, carbonyl pi acid ligand. Okay. So less number of electrons will favor cluster formation, but if there are more number of electrons, the ligand has to be a pi acid. If the ligand is pi acid, there is absolutely no problem. That is second factor. Third factor, what you have told? Size. So instead of saying size, high atomic number. As atomic number down the group increases, stability increases. I'm taking iron and taking ruthenium and taking osmium. Osmium has got a greater effective nuclear charge. Size is also larger. Overlapping will be stronger. Stronger overlapping will be having a more stable bond. Therefore, the stability of a cluster increases down the group. Okay, that is third factor. And the last factor is there should be a suitability between the metal and ligand orbitals that are combining. This example I'll give you in the halide clusters. We have not yet discussed, but I'll give you an example of Re to Cl 2-. What are the number of bonds present between the two rheniums? Can anyone answer? In Re to Cl 2-, how many number of bonds are present between the two rheniums? Re to Cl 2-. This is not the exact structure. It is not square prismatic, it is tetragonal prismatic. There is a difference. This is simple structure that I've given you, where you will find that this is one rhenium unit, another rhenium unit, both are looking to be eclipsed. Both are looking to be planar, but in the true sense they are not planar. They will be like this. Can you see the difference? This is a planar structure. This is not a planar structure. The central point is moving up. This is planar structure. This is non-planar structure. So the central structures are coming close. The edges are going away from one another. It is called as tetragonal structure. Because there is a quadruple bond between the two rheniums, they come so close that chlorine and chlorine, they start repelling one another. They start to move away from one another. So this square will not be like this. It will be like this. This square will be like this. So they move away from one another. But nonetheless, there is a quadruple bond. Okay. So between two rheniums, if at all a quadruple bond has to form, there must be a suitability of the combining metal and ligand orbitals. Only then you will get a quadruple bond. Otherwise, you will not get a quadruple bond. That is a fourth factor. Okay. So just write down the simple factors. Factors affecting the cluster formation. Factors affecting the cluster formation. First factor, low formal oxidation state. Low formal oxidation state. Just a few points about it. If the charge of the metal is high, if the charge of the metal is high, if the charge of the metal is high, comma, size of the orbital, what will happen to the size of the orbital? Charge increases, size of the orbital decreases. The size of the orbital decreases. The size of the orbital decreases. Therefore, overlapping decreases. Therefore, overlapping decreases and stability also decrease. Overlapping decreases and stability also decrease. Stability also decrease. Okay. How to understand it? Suppose if I am taking metal present in 0 oxidation state, its lobe will be larger. Metal present in +1 oxidation state, nuclear charge is increasing, effective nuclear charge will also increase, so the size of the lobe will decrease because there is more attraction. Same number of protons but less number of electrons, attraction will be more, size of the orbital will shrink. When the size of the orbital shrinks, suppose if another metal comes, can they overlap efficiently? No. If they try to come very close to have an efficient overlap, metal will have a nucleus, positive charge. This is a positive charge. When they come much close, repulsive forces will dominate. Whereas if the metal orbital is large, if it is a larger size, two metals need not come close. Repulsions will be less, but overlapping will be strong. So whenever the size is larger, overlapping will be high. So as charge increases, size decreases. Therefore, overlapping decreases. Since overlapping decreases, strength decreases. Strength decreases, stability also decreases. Okay. So what is the factor? Low formal oxidation state will favor stable cluster. Okay. Second, less number of electrons, less number of electrons, less number of electrons. Write a point. If the number of electrons are more, if the number of electrons are more, they enter more number of, if the number of electrons are more, comma, they enter more number of ABMOs, comma, bond order decrease, hence stability of a cluster also decrease. Bond order decrease, hence stability of a cluster also decrease. Okay, so less number of electrons is always favored. More number of electrons, cluster stability will drop. But suppose if there is more number of electron, what type of ligand should be present? Pi acid. Write it in bracket. If it is a more electron system, high electron system, if it is a high electron system, ligand must be a pi acid. Ligand must be a pi acid. Close the bracket. Third factor, high atomic number. High atomic number. Write a point. Down the group, as atomic size increase, comma, effective nuclear charge also increase. As atomic size increase, comma, effective nuclear charge also increase. Therefore overlapping increase, and hence stability also increase. Last factor, suitability of the combining metal ligand orbitals. Suitability of the combining metal ligand orbitals. Okay, that is the last factor. So just we'll close with a small question. Mn2CO10, there are more number. I did not give you the stoichiometry, but just whenever I subject Mn2CO10 photochemically, Hnu refers to photochemically. So whenever I subject it to some photochemistry, that can break. What can break? Two things will break whenever I subject it to a photochemistry. Any metal cluster I take, any carbonyl cluster I take, whenever I subject it to light, either carbonyl will break or metal-metal bond will break. Both can also happen. Okay, so metal-metal bond breakage is one choice. Metal to carbonyl bond breakage is another choice. Here you can see both. One Mn2CO10 is breaking down into MnCO5, 2 units, or in another Mn2CO10, carbonyl has been broken down. Okay, forget about the first one, MnCO5. Look at the second one. Does it obey 18 valence electron rule? Does it obey 18 valence electron rule? No. It is obeying, Mn2CO10 is obeying 18 valence electron rule. We have seen the structure also. Around each manganese there is 18 electron. Mn2CO9? Yes or no? I am not drawing the full structure. We have done it already, just for our understanding. 5 to 10 electrons plus manganese is 7. Manganese is 7 plus 10 electrons. 1 electron is counted from the metal-metal bond. So 10 plus 7 plus 1 is 18. 7 plus 10 plus 1 is also 18. Both manganese are obeying 18 electron rule. In Mn2CO9, does both manganese obey 18 electron rule? If Mn2CO10 is obeying, I remove one carbonyl, does it obey 18 electron rule or not? Yes? They obey. One is bridging. Even if it is bridging, you just check. One is bridging. Okay, you put it bridging. Or should I put one more metal-metal bond? That is not a possibility. Now here you have a unique structure where there is a carbonyl. Mn2CO10, MnCO5, MnCO5. Here also you have MnCO5, but one carbonyl I am writing separately, MnCO4. So around this carbonyl you just check, do you have 18 valence electron? Yes. Manganese is 7, 7 plus 8 is 15, 15 plus 2 is 17, 17 plus 1 is 18. For this manganese, 7 plus 8 is 15, 15 plus 1 is 16 only. For it to satisfy 18 electron rule, it requires 2 more electrons. In such a case, this carbonyl will provide 2 electrons. This carbonyl is providing 2 electrons from a pi bond. From a pi bond. This is a very rare bonding mode of carbonyl. In beginning, we have discussed bonding modes of carbonyls. How many different carbonyls bonding modes are there? Terminal, bridging. In bridging, doubly bridging and triply bridging. But this is a completely different bond. It is a completely different bond. It is not like a doubly bridging or triply bridging. Here it is like a pi bond, or this electron density is being donated to this metal so that it will be satisfying 18 electron rule. It is one of the rare bonding modes of carbonyl. Okay, just write a final point. Write down this question and then write down that point. For a carbonyl, we can write down this question, just leave some space. For a carbonyl, the most common bonding modes, for a carbonyl, the most common bonding modes are terminal and bridging. Terminal and bridging. But the electron density present between carbon and oxygen, can also be donated to a metal, which is a rare bonding mode. It is a neta-2 bonding mode. Neta-2 means dihapto. Both carbon as well as oxygen are involved in it. Therefore, I can call it as neta-2. It is a neta-2 bonding mode. Neta-2. This will come in the organometallic chemistry. It is a neta-2 bonding mode. Okay, you can write down that reaction. So we'll continue in the tomorrow's class with halide clusters.